Let's see what I'm about to talk to you. We will address a very special issue of embedded systems. Embedded systems can be found everywhere. How I would define them is that they are computers, but they are not PCs, not personal computers, which means that they don't have displays or may have displays, but not large displays. They might be having keyboards, but not full-sized keyboards. And they usually do not have these debugging and programming possibilities as others. But even in this case, we have even higher security challenges than in usual cases, namely that these embedded systems, which can be mobile phones, which can be video set-top boxes, game decks, or even industrial controllers, might be occupied by the bad guys, the attackers. And even in the case, if they got into a hostile environment, the security used in them should be strong enough to prevent an attacker to obtain internal secret from the device. And the attacker in this case have many passes, many ways how they can crack the system. We will go through on them, check what are the possibilities of them and what are the possibilities from the security point of view. And at the end of the presentation, I will introduce you to the security testing tools that we apply in the evaluation of these embedded systems and conclude to some experiences of our evaluations. So first of all, let me introduce our research laboratory. Search Lab stands for the Security Evaluation Analysis and Research Laboratory, but we are very specialized in evaluating these embedded systems. We go down to operating system kernels, we go even deeper to motherboards, chipset level, and we also had evaluated several security chipsets when it was really a challenge whether we can get the secret keys out of these smart devices. We are, let's say, internationally recognized because we were involved in the security auditing and evaluating of many operating systems for these embedded devices. We worked, let's say, more than 7 years for Symbian before it was shut down, for Nokia with the S60 platform, with Memo and MiG operating system that were more or less open sourced, but developed by Intel and Nokia. And nowadays, we are also evaluating video set-top boxes. As far as I learned in India, you are just about to turn from the previous. In my introduction, I told you that this is a very special topic because the security challenges are higher than in case of even a web service or web server. In case of a web server, you put the server into a well-protected infrastructure, and you know that the only way an attacker can go in is a cable, is the internet connection. You can apply firewalls to them, you can check this connection on that. In case of embedded system, you do not have this privilege. An attacker can obtain the actual device, can have many surfaces, may try to break into the system on any surface. So these devices should work in a hostile environment, and still they should provide stronger security than other PC-based systems. In my talk, I selected a use case, which is a set-top box, as you can see here, and we will try to disassemble it and show what we can do with this. What is very important that in case of set-top boxes, you may know that there are so-called conditional access system providers which are doing the encryption part of this whole business. Usually they provide a smart card which can be put into the actual set-top box, and this smart card contains the root key. From this root key, they generate a daily key, and from the daily key, they have these so-called control words which are really do the bulk encryption. And these conditional access service providers are very keen on securing their solution, but the actual set-top box vendors do not care about security at all. They care about volumes, they care about the price, the end user price of the devices, so they want to decrease the actual spending, development costs. And the operators who suffer from the financial loss have very limited pressure on the set-top box providers. So that's why we, as an independent security evaluation laboratory, evaluate the set-top boxes whether they comply with the strictest security rules in the name of the operators. So that's why we are acting as a man in the middle between the operators and the set-top box vendor. So an attacker, as I mentioned, has many possibilities to break into such a system. He has physical access to it, and the final goal of these attacks used to be to get out the secret key, which is called control words in the set-top box world. And these control words are used to decrypt the video channels. To reach this, they can use several interfaces. For example, what is the most important is the G tag, which is the debug interface of hardware devices. In this case, they can read out and in some cases even modify internal content of chips. In previous versions, when these G tags were really accessible on the motherboard of the card, it was relatively easy for attackers to break into the system. Nowadays, they are well protected. There are different serial interfaces. As we will see within this device, this is a very low-end set-top box that we just put on the show, has this traditional RS-232 connection to my laptop, so I can open up even a console running on this device. And these serial buses gives very good possibility, standardized buses, very good possibility for attackers to have internal information out of the device. And there are many other external connections depending on the actual set-top box. We may have USB, we may have Ethernet. The latest versions contains also hard drives. A part of the operating system, a part of the application runs from these hard drives. They can record video channels or even video on demand services used by these hard drives. So if we can modify the content of the hard drive, or an attacker can modify the content of the hard drive, this is an attack surface, how he can execute arbitrary code on the target set-top box. And the HDMI, the DVI connections might also have bidirectional access to the set-top box. So what the chipsets and what the vendors do in order to increase the security. The heart of the set-top boxes is one chip, which is a complete system on chip. And the system on chip usually contains a general purpose processor and the security part. The security part do the encryption part, do the security key holdings and everything. They are usually designed in a way to be really strong and really secure. There should be no way to get out the secrets from the chip on the surface of the chip. Maybe if you can somehow have access to the surface of the chip, you may have some chances, but otherwise you don't have possibilities. And this system on chips contains everything that is needed to do this operation, including RAM, flash, all the interface implementations and things like that. And we have security features of this system on chip services like secure unique identifiers, which should be really unique, and usually several encryption techniques depend on the uniqueness of this identification, secure key storage, and the cryptographic engines. But as I mentioned, usually they are really well protected. And what is more important, they have antifuses, which can be thought as one-time programmable memory areas. So they are set during the production, and if they are set, no longer the attacker will not be able to modify them. And they have the so-called secure bootloader, which is responsible to check the integrity of the flash chip, which contains the executable code for the set-top box, which means that the applications running from these memory flashes should be digitally signed and properly verified by the chip itself, and only after a successful verification can be executed on the target system. And for this firmware, which is contained in these flash memory chips, usually professional set-top boxes have additional protection in name of encryption and scrambling and all the other stuff. And we will see later on that this is, let's say, the hardest obstacle, first obstacle for an attacker to get into the system. In many cases, today's security on chip, video security on chip solutions have encryption, on-the-fly encryption of the memory area, which is very important because if the attacker can have any access to the internal bus of the motherboard, even then he will not be able to read out interesting content like videos, plain text videos, or even the encryption keys used for doing the calculations. So in this environment, the latest step in this issue is the so-called chipset pairing. The chipset in this case is not the system on chip, but the smart card, which contains, let's say, the root key, which identifies the subscriber, and the operator can decide, based on this identification, whether a certain set-top box should be able to decrypt the videos or not. Let's see what we can do in this environment when we have to implement very strong security. So this challenge is challenging also from us, for evaluators, because if everything would be done properly, we should have to do nothing with these actual set-top boxes. And if we cannot do anything and maybe can bypass the first protection, they may get into the chipset. So that's why we developed a so-called man-in-the-middle flash manipulator tool, which you can just see on the screen. We have this man-in-the-middle type of evaluation tools for almost all of the interfaces, for serial cables and all the other stuff. So we can, on one hand, monitor what is going on from electrical point of view, and we can, in some cases, even manipulate those. And we also have the usual monitoring devices. We have a university in a nearby, so we can use X-ray images just to detect where are, for example, the G-tag connection points, which were developed for development purposes, and in several cases during the production version they can be found, but usually these connections are not mounted. We have to mount it after then, and we can have access to the G-tags. And here you can see an example. Well, this is another embedded device. This is a mobile phone, not a set-top box, but we managed to connect to them as well. We have a special possibility to dismount chips from the motherboard, and instead of this chip, we can have wires, and therefore we can monitor the connection. For example, in this case, with this mobile phone and its memory chip. Here you can see it from the back, that this is the way how we connect them to the actual device. And therefore, this is a way how it boots up things, and we have an analyzer, logic analyzer, which really can record everything that is going on. Okay, let's turning back to this flash manipulator that I just want to show you and demonstrate how it works. The architectural structures looks like this. Here is the original printed circuit board or motherboard of the set-top box. We desolder the memory flash chip from the motherboard and have wires instead of each of the pins of this memory chip. Have this connection to one of the ports of our flash manipulator. And this flash manipulator have other ports, port 1 and port 3, as you will see. And we can connect the original flash chip to one port, and we can have a modified content with the same flash chip to another port. How we do is we buy or we require the actual vendors to provide us not just one set-top box, but many. So practically here, for example, in this example, as I thought, we have 3 pieces of these flash chips, and they are originating from 3 well-equipped set-top boxes. This is the best way to get exactly the same chips with the same hardware behavior, and we can modify one or the other's content. And we do have a freely programmable Xilinx processor on it, because in this case it is really fast. So we can define several algorithms which can, on one hand, select from the data bus what to record. We can define special triggers when we have to change from the original flash to the modified flash. And we also have 2 megabytes of RAM just to record the bus traffic. You know, this bus traffic is very fast. There's no possibility to send this information to the PC. So usually what we do is to record the bus traffic, and after then we analyze it from the PC, and for the PC we have a USB connection. So here is it in a picture, how it can be seen, and you can see it in live. And maybe I can ask the technical guys to try to switch my screen to this demonstration image. Can you do that? Okay. Let's see what you can see. Can you come closer a little bit? Do you have a light? Light. Oh. Okay, so I guess it's better. So this is the set-top box, and that was the original place of the memory chip. We desoldered it, dismounted from the motherboard, and mounted a special connection to it. So this was also. And this is the flash manipulator tool, which has 3 ports. One goes to the original part, and the second goes there. And we have 3 different versions of the memory chip. Maybe you can see this is the good 1, good 2, and the modified version. And for the first trial, I will connect the original memory flashes to these ports. Start the flash manipulator. It flashes. And can we solve that on one of the screen you put my laptop, and the other will be the camera picture? No? Then please turn to the laptop. Can you turn the screen to the laptop? Okay, here you are. Oh. No, that's not it. I need my laptop screen. Yeah, here you are. So I open up a console with a serial connection to the motherboard. As I mentioned, this was done just for debugging the set-top box. And if I boot the set-top box up, yeah, you can see that it's booting. May I get back my... Yeah. Oh, we just missed. And it starts to load the Linux-based operating system. So, which means that we manage another one, which contains a modified content. And start to boot it up. May I see the notebook screen? Okay, when I try to boot up the set-top box, you should see that nothing happens, because we replaced the modified content, and the bootloader recognized that it has been changed, and therefore nothing is executed. Nothing is loaded. So that's why what we do is that we attach the original contented memory chip to the port 1. And the modified one to the second port. Okay, may I get back my screen? And yeah, it's still booting up, but you can see that it tries to load the modified image, which we just replaced as a string. And yeah, let's see what happened. I tried to scroll back the screen to the very, very beginning of the loading, because you can see here what we have done. Yeah, it was the second boot, starting from here. Yeah, here was that part which was booted, and you can see that we injected our own code in it, and displaying that welcome nullcon, we are demonstrating boot from fresh race conditional attack, which means that during the boot check, we showed the original content in memory flash. After then, we turned to the modified version, and we were able to execute arbitrary code. So thank you very much. And let's turn back. So what we gain with this, that we are able, with this tool, all the traffic going on in the bus. So we see whether all the developers were cautious in keeping all the secrets really within the chip, and nothing goes out on the accessible internal bus. We can switch between original and modified shares, execute arbitrary code, so we can test the actual device within. Okay. So the experiences. What we found out after evaluating several set-top boxes, that there are many easily readable strings, debug strings in it, which help attackers to access internal functions in the solutions. They told us, in many cases, a lot. So if you would like to develop a more secure product, usually that's the first thing that you should do, remove all debugging information from it. In many cases, we found out that the GTAG debug ports were open, which let attackers into the chip, not just to the motherboard, but within the chip. And with this bootloader, which was about to check the digital signature of the flash, we could figure out by modifying certain parts of the image that in many cases, not the whole image was digitally signed, but certain parts of it. For example, in some cases, you may know that there are so-called splash images, which just displays the operator logo, which is customized according to different operators, are not digitally signed. And within the splash image, you may execute arbitrary code, and therefore an attacker can do the same. And in many cases, we found out that exploitable security vulnerabilities, like the zlib expression compression, compression and decompression library that contain a buffer overflow, was still exploitable in this platform, which means that even the image, which was digitally signed, contained this buffer overflow. The actual bootloader first started to decompress the image and check the digital signature only afterwards. And during the decompression, we could apply the buffer overflow and get into the system bypassing the digital signature. And we found out various problems with this digital signature verification. We saw even case when the private key was also stored with the public key on the system, which checked because the actual programmer did not understand the basics of the public encryption. And we also found examples when they used example public keys from the open source development library. So we could find the secret key pair on the internet for the actual public key that was used for digital signing. And we also figured out weak methods, obscurity, security by obscurity solutions, and things like that. We also could find out operating system vulnerabilities in this way when everything was executed as root. So every executable that was put onto the image was easily executable. We may see debug consoles like we just saw in this case of the set-top box, which is very easily accessible. And in many cases, if the boot fails, the set-top box turns to a safe mode and uploads an image without any checking of the digital signature. So the attacker can still go into the system. And if we do have a hard drive, the attack passes are even more. We can replace any file on the hard drive if they can somehow influence the execution of the set-top box operation. We could also break into the system. So what is very important, collecting all those examples and all those results, that in this environment, which is even challenging from security point of view than usual PC-based systems, we do have the testing capabilities. Attackers do have the potential to break into the system. And because there is an industry of selling video broadband distribution access on a relatively free basis, this is really a challenging issue. And I really hope that you could check and see what are our capabilities as a laboratory and what we do as an evaluation and certification laboratory for this industry. So thank you very much, and I'm ready here for your questions.
It's a mass penetration device. Basically you have to put it to so many consumers. It has to come at a very reasonable price. Now, when you start building in so much security into the device, say if a device costs X, what would be the new price for the device? Because the question is, technology has to be affordable, especially in this space. So how do you keep the cost down as well as increase the security? And from your experience, what percentage basis the cost would go up for the end consumer?
Yeah, because everything is integrated into one chip. This is how we call it a security system on chip. Usually these chip vendors invest a lot into security. And after then, the set-top box vendors who produce the motherboard, the packaging, and everything goes down with prices. That's the way how we can do that. Usually we evaluate the chipsets differently. They get a certification. And after then, the set-top box is evaluated according to the chipset they use. So if the chipset doesn't get a certain level of certification, the set-top box cannot do that. And usually what we check is whether the set-top box vendors comply with all the security guidelines of the certain chipset.
That's basically my question. Like, what would become the differential in price if I incorporated security features?
I'm sorry, this is not a commercial presentation. I can't answer that question, but we have a fixed price for the evaluations. So we have a certain criteria that we should go through if a set-top box vendor complies with the requirements or not for certain levels. We have 10 levels. Yeah?
You made some statements like the public key and private key are stored at the same place, and they are using encryption via obfuscation. So is that true with most of the vendors, or?
As you can see, we are over, or you can't see right now, but on my summary slide it said that we are over 100 set-top box evaluations, and half of them failed, and not just because one reason. So this means that, let's say, almost half of them passed through, but our experiences shows that in many cases the developers were not security experts, even though they develop a security product. A set-top box is a security product. It does encryption and decryption, nothing more. That's what it's meant for. And even then, the implementers are not in the position, not in the knowledge. That's why it's very important to evaluate these set-top boxes and do not believe them.